we're gonna go through these. We'll take as much time as we need to, ask questions as you need to. We talked about these a little bit. So reminder, chapter 4, we're talking about covalent bonds here. We're talking about how atoms share electrons to form a covalent bond. We talked a whole lot about Lewis structures and how Lewis structures help us visualize how the atoms are connected together and arranged. And we said a condensed structure has a shorthand notation. It allows us to imagine how the atoms are connected. So it is not a Lewis structure. It's almost more similar to what we call a molecular formula, okay? And a molecular formula just tells us how many atoms and what kinds of atoms are in the molecule. But we have no idea how they're arranged. The difference between a molecular formula, okay, and a condensed structure is we can know exactly how things are connected. We can imagine that from the condensed structure in a way that we cannot, and we're kind of doing more guesswork with a molecular formula. So, for example, the way we read these condensed structures is in groups. We have what we call the main chain, and then we have atoms that are branched off of the main chain. And we need to remind ourselves, how do we differentiate between atoms that are part of the main chain versus atoms that cannot be in the main chain? Okay, so if we have main chain, and I'm going to say branched atoms. Okay, which ones can be main chain, which ones can be branched? How do we know? Well, any atom that can form more than one bond could be main chain. So these are atoms that can have, I'm going to say more than one bond, okay, greater than one bond. And branched atoms, these are atoms with only one, they can only form one bond, okay? So good main chain atoms, we'll write them in parentheses up here above. That could be carbon. Carbon is a great main chain atom because it can form 4 bonds. Nitrogen can form 3 bonds. Phosphorus can form 3 bonds. Silicon is below carbon. It's same group. It can form 4 bonds. What else? Oxygen and sulfur. Okay, these are not everything, but these are the very common ones. Which atoms can be branched atoms, or only will be branched atoms? That's going to be hydrogen, and that's going to be your halogens. Okay, these guys can only form one bond, so they'll never be central or main chain atoms. Okay. Now remember that once you find a main chain atom, it is connected to the next main chain atom. So if we are imagining this big structure down here, C8H18O, we see the condensed structure for it, and now we start to read it in groups. I'm going to draw a line between every group, and I am actually going to change to pink for this. Okay, these lines are going to separate your groups. Okay, and the first atom listed is always the main chain atom in the group. Okay, so if we start drawing lines between the groups, now we can read them. We have a CH3 group, and you can start to draw that. I'm gonna, you draw your hydrogens in too. Then we have a CH2 group. And what we said is that the first main chain atom is connected to the second main chain atom, okay? The first atom in each of these groups, as we've separated them, is always part of the main chain, all right? And then you branch things up or down because the way you should draw these is from left to right. Oh, Lord, left to right. Okay, wow, I should have charged my Apple Pencil. This is gonna be bad news bears. I'm gonna talk for a second, and I'm gonna plug it up, and then as I need it, I'm gonna unplug it, and we'll keep going. So that is a little bit of condensed structures. What we're about to do is draw some of these out, and I know we started to get into this, what was that, last Thursday. I'm going to pick 3 of these to do, and then I want you to practice and attempt the other 3 on your own, okay? And if you have questions about any of them, shoot me an email. I don't plan to record videos and give you the answers, but if you want the answer for any particular one, don't hesitate to ask for that. So before we dive into this, though, you can see there's parentheses, and there's 2 ways you can use parentheses in condensed structures, okay? The first way is demonstrated in A right here, okay? This is one way to use parentheses. When you have a group that is identical and you have multiple of those groups, you can use parentheses if they're all connected one to the other. Immediately, like in a row. Okay, so for example, if we expanded, we're going to do A right here. If we expanded A, we would have CH3. That's our first group. Now, what's in the parentheses is an identical group, CH2. And what this subscript 3 means, sorry, I'm supposed to be in dark green, aren't I? What that 3 means is that there's 3 CH2 groups right in a row, bam, bam, bam. Okay, so I'm now going to draw those CH2 groups. And there they are, okay? And you could even box them in if it helps you see. Here's our 3 groups, and the main chain carbons are just connected there. So that's one way you can use parentheses, is to do that. And then obviously at the terminus of this molecule, you have another CH3 group. That's kind of, the CH3 groups are the bookends per se to this molecule. Okay, so that's one way. But there's another way. There's another way to do it as well, and that is a good example is letter E. So let's look at E. We'll do E and F. B, C, and D, I would like for you to try on your own. So let's do E. E looks pretty long and pretty hard. But first, let's go in and kind of divide up the groups. I'm going to go back to pink because I thought it's a better contrast for just a second. Here's one group. Now, let me point out the parentheses thing here. You see this oxygen in parentheses. Oxygen can be a main chain element, but when it's in parentheses, it is branched, okay? So when you have an element, or even sometimes you'll see like an OH group that's branched, that's in parentheses, that means it is branched off of the main chain atom that comes before it, okay? So this oxygen is going to be branched up or down off of this second carbon here. So I'm going to put a line on the other side of the oxygen because that carbon and the branched group of their own. And then I'm going to separate out my groups. Here's another oxygen in parentheses. Okay, now I'm also going to isolate this oxygen is going to be a group of its own. It's part of the main chain. It's not in parentheses, and it can have more than one bond. So it's just going to be a continuation of our main chain. And so there's our groups. I've divided up our groups. Now it's just up to us to connect the groups, okay, to write them properly and to connect them. So go back to dark green. All right, I'm going to kind of draw it up here in the space above. So we got a CH3 group. Then we have a carbon. Now we're in the second group, and we have an oxygen in parentheses. It doesn't matter if you branch it up or down, but what do you know about oxygen? What does oxygen need to look like in a Lewis structure? Anybody remind me? How many bonds, how many lone pairs? That's what I'm really asking. Two bonds and 2 lone pairs. Okay, so we need to make sure we give oxygen, and oxygen is just connected to that carbon. So we're going to connect it there, just like that. So that's group number 2. So this was group 1, this is group 2. Now we're going to draw group number 3. So C, H, and H, CH2. We have another CH2 group. I'll call that group 4. And then we're on group number 5, which is a carbon. Doesn't matter whether you branch this oxygen up or down, it's going to look just like group number 2. We know oxygen has 2 bonds, 2 lone pairs. Number 6 is just an oxygen. So I'm just going to continue the main chain here, draw in my oxygen. We know oxygen, again, still same rules, 2 bonds and 2 lone pairs. It's just that here the bonds are single bonds. Whoops. So we're going to connect group 6 to group 7. And I need to go back and put lone pairs on my oxygen. Okay. So let's look at that. That was kind of fast, probably. Here's where people run into problems, is separating the groups properly. Okay, if this helps you to separate it into groups, you have to make sure you understand when something is branched off the main chain, when it's in parentheses, or when it is a continuation of the main chain. If it can be an atom with more than 1 bond, so 2, 3, 4 bonds, and it's just going to continue the main chain, or if it's supposed to be branched off. And if it's supposed to be branched off, it's in parentheses. Okay, so again, there's 2 ways to use parentheses. We looked at an example of both. Now let's do F. Okay, F looked really hard. Everybody voted F in the first morning section. So what do you have? You have another use of parentheses here, and these parentheses have a subscript, which means we have two of an identical group. But what is it attached to? You're used to seeing these groups attached to or a continuation of one another. Okay, like up here when we did A, we just said these were three groups right in a row, bam, bam, bam. Well, that's here in this case, these two groups are attached off of this carbon. Okay, how do we know that? Well, we have to kind of look at the structure as a whole and say, this carbon right here, I know it's connected to this oxygen, but I don't have anything else on the other side of that oxygen. And I know this oxygen just can't have one bond. This oxygen ends the molecule. So that oxygen has to be double bonded to the carbon. I know I have that. And so what are we missing? Well, this carbon as drawn only has 2 bonds so far. And I know that carbon has to have 4 bonds. All right. So because I have 2 of these groups, that's how I'm going to guess that these 2 groups are also bonded to this carbon, because I've got to have 2 more bonds on the carbon. So let's start drawing what this would look like. The group in the parentheses is a CH3CH2O. So let's look at that. I'm gonna even separate this parentheses into its own groups. Okay. All right. So I have I'm gonna call this carbon 1 and carbon 2 in my group here. So I have my carbon 1, which is a CH3. Then I have a CH2. Okay, that's carbon. That leads us to our second carbon. So there's my C with an H up and an H down. That's a CH2. Then I have an oxygen. Okay. Now, if I double bonded this oxygen to this carbon, would that be correct? Could I then continue my structure? No, I cannot. I've just run into a dead end, essentially. I've dead ended the molecule because I can't put another bond on that oxygen. Oxygen can only have 2 bonds and 2 lone pairs. And if you're cloudy on these things, or how do I know these things, go back and review the content from last Thursday, where we kind of drew out that guide and that key for what all these types of atoms should look like in a Lewis structure. All right, so I know that I cannot, let's undo that. I know it's got to look like this. So now I'm going to connect, I'm going to zoom in, I'm going to connect, let's pick a wildly different color, blue. I'm going to connect this oxygen to this carbon, okay? Because this carbon still needs 2 bonds, and that oxygen still needs a bond. So I'm just going to connect it to that carbon, and I know that I have this in my molecule. There it is. Okay, but we only have 1 of our groups. Okay, remember we have 2 of these because there's a subscript 2 that I'm circling. So I've got to draw another one of these groups. And when I say these groups, what do I mean? I mean this whole group right here. I have another one. Where am I going to put it? Well, you can either branch it up off of this carbon, or you can branch it down. And since I just drew that arrow, I guess I'm going to branch it down. So I'm going to draw an identical group. I know that carbon is bonded to an oxygen, and then I have a CH2 group, and I have a CH3 group. Okay. So these condensed structures, and I'm going to circle this, you can see, oh, and what did I forget? What do I not have? I'm missing something. What's the last thing I need to do on these?
Put your lone pairs on the oxygen.
Put my lone pairs on my oxygens, okay? So I'm going to add those in right there.
When we're writing our answers for these, do we always have to add the lone pairs?
Yes. Yeah. Yep, and make sure you do that. I made sure to put that as part of the instructions for the lab that you're going to do. Make sure you do that for the lab as well. You always have to put lone pairs in. Because that's going to just help you keep track of the amount of valence electrons that should be in these things anyways. So the 2 things that I boxed in pink, you should see that they're identical groups. And that's what these parentheses and that subscript of 2 were indicating. So if I erase, I'm trying to charge this pencil as much as possible. I don't want it to run out. Okay, questions, any other questions on these structures? Again, try B, C, and D for yourself. All right, so we're gonna move on. That's the end of condensed structures, and now let's talk about geometry. So geometry, I'm gonna chat for just a second. So far, all we've been looking at molecules is through a lens of a two-dimensional perspective, okay? And even Lewis structures, like we can see how they're connected, but it's only 2 dimensions. Well, molecules are not 2-dimensional, they're 3-dimensional. We're made up of molecules, we're 3-dimensional. We need to understand molecules in 3 dimensions so that you understand the shape of them. That's going to help us know how they interact. So that's why we're talking about molecular geometry. So we've kind of paused and put a pin in condensed structures and Lewis structures. Now we're moving on to a new topic, molecular geometry. So Lewis structures, I'm just reading the screen here. They help us keep track of valence electrons and the geometry or the shape of the molecule. And it's electrons, their location, that determines the shape. Or you could write geometry. Okay. So as usual, electrons are responsible for like everything. Now I want to point out this figure right below. You see several different molecules, and it's starting to show you the 3-dimensional shapes. It's trying to indicate 3 dimensions. You can see that these molecules are different based on the number of spheres and the colors of the spheres. So anything that's white, a white sphere is a hydrogen, and then the colored spheres represent different elements. So like this first molecule on the left, methane, CH4, if you're looking at the slide, the black sphere would be carbon, and then those 4 white spheres are hydrogen. Now, as we go across and we look at ammonia and water and hydrochloric acid, there's something that we're not seeing on these structures, okay? So I want to talk about what is visible and what is invisible when we actually draw the structure and we see its geometry. What should we draw? What should we not draw? Okay, what's visible are the atoms and the bonds. What's not visible are the lone pairs. Okay, so for example, well, CH4 doesn't have any lone pairs, so let's look at ammonia, NH3. What do you know about nitrogen? Okay, nitrogen should always have 3 bonds and a lone pair. How do we know that? Well, when we understand covalent bonds and the octet rule, here's just a recap and a reminder. Nitrogen has 5 valence electrons, okay? And so how many does it need? We always have to ask ourselves that question. How many does it need to get 8? Well, it needs 3 more. And remember, the number of bonds that an atom forms matches the number of valence electrons that it needs. So there's the 3 bonded hydrogens on this nitrogen, but it has a lone pair. It has a pair of electrons that it's not sharing, okay? And I'll just draw that in, put a little cloud around it. So we don't see that lone pair when we actually draw the molecule out, but it is there, and that lone pair does help force the geometry. And so we can't ignore the lone pair, it's just that we don't draw them in the final imagination of the molecule. That's because electrons, again, they're always moving, and we can't exactly visualize them as a static thing, even though sometimes we draw them that way. What about water? Okay, we know oxygen has 2 bonds, 2 lone pairs. So water should look, the oxygen at least, kind of has these Mickey Mouse ears. This made me, speaking of Mickey Mouse ears, I got my daughter a Elsa Halloween costume because she loves Frozen. And I just happened to see one at Walmart, and I was like, easy done. She was a taco last year, and a felt taco. It was the cutest thing. So I got her this Elsa dress. I was so excited to show it to her, and I came home from Walmart, and I was like, Finn, her name is Finley. I said, do you want to be Elsa for Halloween? I showed her the dress, and she goes, no. I was like, well, okay. Well, it won't fit me, so it looks like, and so we decided she will warm up to it, I'm hoping. So I'm not taking it back, sorry. So she's going to be Elsa is the goal, and then our newborn is going to be Olaf. So if anybody has cute suggestions for how to do a baby snowman. And then I told my husband he has to wear the headband reindeer ears to be Sven. He wasn't thrilled. Maybe she wants to be a taco again. I will say that was a killer Halloween costume. I literally spent $5 on it. I just bought some felt and like glued it all together. Sorry, the two lone pairs made me think of reindeer ears. How did that happen? I don't know. But anyways, moving on back to molecules. This whole kind of thing, the molecular geometry, it is summarized by what it's known as the VSEPR model. Okay, so what the heck does VSEPR mean? It stands for valence, shell, electron, pair, repulsion. All right. Valence shell, electron pair, repulsion. So what that is saying and what that's indicating is it wants you to understand, again, it's pointing to the fact that electrons determine the shape. Why is that? Well, electron lone pairs, and remember bonds are made of electrons. There's two electrons in every bond. They are all negatively charged, and things that have negative charge, like charges, repel one another. All right, and that's what causes things to move as far apart as they can get from around the central atom, and that's what forces the shape and creates the shape. And that's essentially what this slide is saying down here at the bottom. If you read those bullet points, is that the electrons, they repel each other, things get as far apart as possible. That is what forces the geometry. Okay. Questions so far on just the general concept behind what we're going to get into? Okay. So kind of like with Lewis structures, we had 5 rules for how to draw these things. And for the VSEPR model, for geometry, we got 3 main rules here. And if you understand and get these 3 rules, then naming the geometry will become pretty straightforward, pretty easy. And I'm sorry, now I just need to check how much battery does our pencil have. It's going to drive me nuts. 25%. Okay, we're better. I'm like, is it still at 3%? All right. Number 1, you're going to draw the Lewis structure. And then you're going to locate, you're going to determine what atom am I going to name? What atom am I going to name the geometry for? It's usually the central atom. Atom or atoms, okay? There can be more than one central atom, and we'll look at an example in a little bit. You're never going to name the geometry for a perimeter atom, okay? You might want to take a note on that. We're not naming geometry for perimeter atoms, just for central atoms. Rule number 2, find the number of, here's a new term, charge clouds. What in the world is a charge cloud, okay? So you're going to find the number of charge clouds on the central atom. So a charge cloud can be 2 things. It can be a bond or a lone pair. Now let me explain something with bonds, because here's where charge clouds get confusing. A bond is treated, whether it's a double, a triple, or a single bond, we treat it equally. They're all 1 charge cloud each. Even though there's different number of bonds in a double bond and a triple bond, it's just 1 charge cloud. So that's what this bullet point is saying. Bonds, including double and triple bonds, they all count as 1 charge cloud. All right, so this is just equal to 1. That is 1. I'm going to abbreviate charge cloud. All right, and this, a double bond, that is just 1 charge cloud, just like a single bond is. Lone pairs as well. And remember, a pair is 2 electrons. So a pair of 2 electrons is 1 charge cloud. All right. Once you have done those 2 things, you're going to predict the shape. And how do we do that? You have this table. I think someone from the morning lecture said this is on page 118. So if you have your textbook, I encourage you to flip open to page 118. This table is going to be very helpful for you. So it's in your lecture notes here. It's in your textbook. When the exam comes, use this table, okay? But I will also encourage you to memorize some of this stuff so that you don't have to go digging for it and things are more quick. Oh, here was another thing about exam 1. I noticed on some people's pictures of their problems, they spent the time to write down the whole problem. And that really confused me. Why do you need to write down the whole problem? Some of these were long word problems, which is taking up minutes of your exam time. So I didn't understand why people would take time to write the problem down. I don't know, but that's just another thing that caused me to raise a little eyebrow, but if it helped you, you do it, I guess. All right, let's talk about this table. I actually kind of have a bone to pick with this table. It says number of bonds, and I'm going to edit this. I want you to, and I'm going to use this phrase a lot. Instead of number of bonds, I wish it said number of bonded atoms. Okay, so pretend it says that. And that is number of bonded atoms to the central atom. How many atoms are bonded to our central atom? So let's look at the first row here. We're actually going to walk through these step by step. All I want you to know is that you look at the number of bonded atoms, you look at how many lone pairs are on the central atom, okay, and you add those two things together. So for this whole table, you're going to add column 1 to column 2, and that will give you the answer for column 3, okay? So the number of bonded atoms plus the number of lone pairs tells you how many charge clouds are on your central atom. Then you just look at what the geometry name is supposed to be. If you have 2 charge clouds, we only have one geometry here. It's called linear, all right? And here's what it looks like. That means that these bonded atoms are as far apart as they can get. And as far apart as they can get is 180 degrees. And then it gives you an example molecule over here. Carbon dioxide is a great example. Now, I bet you're looking at this molecule thinking, I know there's lone pairs on this molecule. And you're right, there are lone pairs all over these oxygens, right? But remember, it's not the perimeter atoms we're naming. So we don't count lone pairs on perimeter atoms. We just count lone pairs on the central atoms, and carbon has 0. Okay, so remember that. There's 2 ways that things can add up to a total of 3 charge clouds. You could have 3 bonded atoms and 0 lone pairs, or you could have 2 bonded atoms and 1 lone pair. If you have the first case scenario, 3 bonded atoms, no lone pairs, here's the name. Now, people, here's what I miss about being in person. I miss the way you guys would all incorrectly pronounce this. Okay, sorry, I don't make fun of you, but, you know, I want you to say it with me. It's trigonal planar, not trigonal, not, everybody say it with me. 1, 2, 3. Trigonal, say it in your dorm room by yourself. Trigonal planar, okay, thank you. A good example is a carbon with 2 hydrogens and an oxygen. What do these dashes and wedges mean? They're trying to indicate 3 dimensions. All right, the hydrogen with the dash would be back. It'd be pointing backwards behind the plane of the screen. And then the carbon with the wedge is forward. Okay, it's like it would be coming out of the plane towards us, or off your paper towards you. And then the carbon and the oxygen would be in the same plane. So it's just trying to indicate 3 dimensions. All right. If you also have 2 bonded atoms, 1 lone pair, 3 charge clouds, you can be bent. Okay, the lone pair here, lone pairs are kind of pushy. They push atoms around, and they actually force them to be closer together than they really want to be. You'll notice down here we can have a geometry of bent with 2 bonded atoms and 2 lone pairs. But anyways, that's 3 charge clouds. 4 charge clouds. There's 3 different ways things can add up to have 4 charge clouds. You could have 4 bonded atoms. A great example of this is carbon. We know carbon always has 4 bonds and no lone pairs. Now, carbon doesn't always have 4 single bonds, but a lot of the time it does. Okay, so 4 bonded atoms, no lone pairs, 4 charge clouds. We call that tetrahedral. And again, here's kind of our poster child for that. Carbon with 4 hydrogens, molecule of methane. And then 3 bonded atoms, 1 lone pair. Let's see, nitrogen. This is like, nitrogen is pyramidal almost all the time. I say almost because not always, but a lot of the time it is. And then I already talked about this bit. So we're actually going to review everything we just went over in this table in these coming slides. So 2 charge clouds. We said 2 bonds and 0 lone pairs. We said this is linear. And this is just giving you more examples. All right. We said the bonded atoms, the farthest they can be apart is 180 degrees. Now, do not waste your time memorizing all these bond angles. I think it will help you visualize it for these slides, but I'm not going to ask you about bond angles on the exam. So HCN is a great example. Again, just because you have lone pairs on the perimeter atoms, that does not necessarily affect your geometry for your central atom. We're just naming the geometry for the central atom, which is carbon here. And then carbon dioxide, again, is a great example, okay? Questions on linear and how we name it. Now, here's why I edited the table above, because you look at this carbon and you think, okay, there's 4 bonds, okay, so that should be tetrahedral, but it's not, it's two double bonds. And remember that a double bond, just like a triple bond, this right here, we would just say this is one charge cloud. This right here, this is just one charge cloud. And so that just adds up to 2. Even though there are 4 bonds, okay? That's why I look at the number of bonded atoms. I have 2 bonded atoms on my carbon. If we have 3 bonded atoms and 0 lone pairs, we said this is, remember, did you say it right in your head? Trigonal, or did you say trigonal? You said trigonal. Trigonal planar. This is showing you, it's called formaldehyde. I promise I don't have COVID. I just can't get this tickle out of my throat. You have a carbon with 2 hydrogens and an oxygen, okay? Now they're roughly 120. What's the farthest apart you could spread these 3 bonded atoms? It's about 120 degrees, okay? And so that's what this is saying over here, roughly 120 degrees spread out around the carbon. So this first one up here is a top view, and then we have a side view. Remember, those dashes and wedges are trying to indicate 3 dimensions. All right, so that's trigonal planar. Moving on, we're still talking about 3 charge clouds here. If you have 2 bonded atoms, but this time you do have a lone pair, we call that bent. Okay, now why is this one different than the one before it? Okay, well, you can see how the number of bonded atoms and lone pairs is different, but why is the visual different? Because remember, you don't draw in the lone pair. So as we're visualizing this molecule, we just have this bent shape, okay? Compared to up here, we have 3 bonded atoms and we have to draw in all those atoms. So SO2, someone was asking, why is there only 1 bond on this oxygen here? And the answer for that goes beyond the scope of this class. If you've ever taken like AP chemistry or something, you've probably heard the term resonance. And this happens to be a molecule that has resonance, okay? So what that means is electrons are always moving, and at any given point in time, notice we've got 3 lone pairs on this oxygen. One of these lone pairs jumps down here, forms a double bond, and it pushes the electrons in one of these bonds onto the oxygen. And it just kind of seesaws like that back and forth because of resonance. But don't worry about any of that. Somebody was really confused why oxygen had 1 bond, and I wanted to explain it. All that to say is this has been 2 bonded atoms, 1 lone pair. Here's a visual of a molecule like that. Okay, 4 charge clouds. So remember, there's 3 different ways this can happen. The first way would be 4 bonded atoms, 0 lone pairs. This is called tetrahedral. So why do we name it a tetrahedral? Well, if you've ever had geometry, in the central atom, or a tetrahedron is it's a shape that has 4 sides to it. And so if you actually were to draw planes onto this molecule, you would have 4 planes that come together to form the shape. The bond angle here is smaller, right? The more things you attach to that central atom, the less room they have to spread out. So we saw when we had 3 bonded with 2 bonded atoms, they could spread out 180 degrees. With 3 bonded atoms, they could only get 120 degrees apart. Here, they can only get about 110 degrees apart. They're closer together. All right, and again, carbon commonly forms tetrahedrons, but not always. It could also be trigonal planar. Carbon could be linear as well. 3 bonded atoms, 1 lone pair. We said this is pyramidal. All right, nitrogen, like 90% of the time, nitrogen or phosphorus look like this. And again, when you visualize the actual molecule, you don't draw in the lone pair. You just see the atoms and the bonds. Okay. Now again, here's another example of these electrons and how pushy they are. It's not a huge difference, we have 4 things attached to the central atom up here with the tetrahedral. Well, we also have 4 things attached to the central atom. It's just that one of them is a lone pair. And you can see how this lone pair is forcing all these hydrogens a little bit closer together than they would be if it was a true tetrahedral. Okay, 109.5 versus 107. Electrons are just kind of pushy like that. And then lastly, because we have 2 lone pairs, and so that's really pushy, they're forcing these hydrogens as close together as we'll get any bonded atoms, 104.5 degrees. And we call this bent. 2 bonded atoms, 2 lone pairs is bent. So remember, there's 2 ways we can have a bent geometry, just depending on the different number of lone pairs. Okay, here's a review slide. All the different ways you can have 4 charge clouds. Okay, it's just a review all in one slide. All right, so that's it for geometry. There's more geometries than this. If you've ever had, I don't know, if you take another chemistry class, you might recognize there's more. We have octahedrons and things like that, but these geometries are the only ones we'll cover in this course. All right, now what happens when you have a molecule that has more than one central atom? Okay, we say that molecule has multiple centers, in other words. Well, you can name each central atom. Each atom that is a central atom can have a unique geometry. So just because you have 2 carbons in the same molecule and they're both central atoms does not mean that they're both tetrahedral. You have to count charge clouds for each unique central atom. Here's an example. If we have, this is a molecule of what we call acetic acid. It's the acid in vinegar. And if you, well, actually, no, it's not. Sorry, it looks very similar to it. If you look at this, we have a carbon here on the left and a carbon on the right. So this carbon on the left is a tetrahedral. Why? If you count the number of bonds, there's 1, 2, 3, or bonded atoms, I should say. You have 4 bonded atoms. You have 4 single bonds on this carbon. But if you look at the carbon on the left, it's trigonal planar. Why is that? Well, it only has 3. 1, 2, 3 bonded atoms. It just so if there's 4 bonds on both carbons, we have not violated any of the carbons with numbers of bonds. We're satisfying octets on all the carbons here. It's just that you have this double bond between that carbon and oxygen, all right? And that still only counts as 1 charge cloud. Questions on unique geometries for central atoms? Okay, well now we're gonna practice. So get some paper out, grab a pencil. Here's the rules again. I just have everything filled in for you. Let's actually draw some of these out. So rule number 1 said to draw the Lewis structure. And remember, the first rule for drawing a Lewis structure is figure out how many valence electrons you have. So I'm actually going to start there. I'm going to quickly add that up. Then we're going to start connecting atoms. Make sure we have all of our electrons represented. And then we will count charge clouds and we will name the geometries. So now's a good time if you have your textbook, turn to page 118. I think that's where that table is. Or pull that table out from earlier, you may find it handy. So we have 3 carbons. Each one has 4 valence electrons. Hydrogen, we have 8 of them. Each one has 1 valence. Oxygen, we just have 1. Each one has 6 valence. So that's a total of 26 valence electrons. That's how many we need to have in our structure. So remember from last Thursday, I like to just go ahead and start connecting your carbons. And we know oxygen is also usually is going to have more than 1 bond. So I'm going to go ahead and connect an oxygen here, and then we'll just fill in the hydrogens. So I'm just going to put a hydrogen.
Why did we start with the carbon?
Why did we start with carbon?
Yeah. Like, was there a rule about that earlier that I missed?
No, it was the first atom listed, and I know it's the central atom. So I like to start with my central atoms and then branch everything off of them.
Oh, okay, so it's a central atom. Okay, that makes sense.
Yep. Yeah, you'll never see carbon as a perimeter atom. Why? Because you could never have a carbon with 4 bonds like that. Well, I'll never say never. There might be a molecule somewhere, but that would be a rare species. We won't see one like that in this class. And then I'm just going to put hydrogens anywhere I can. So that is 7 hydrogens, and then we need one off of this oxygen as well, and that oxygen needs 2 lone pairs. So I'm just making sure the octet rule is satisfied with everything. Every carbon has 4 bonds. Go back and double check. Every hydrogen has a single bond. Every oxygen has 2 bonds, 2 lone pairs. Do I have 26? You can count them in your head. I'm going to count them in my head. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Yeah, I counted 26. Okay, remember every dash, every line represents 2 electrons. So now let's name the geometries. So how do we do that? Well, we did step 1, check. Now we're going to do step 2, find the number of charge clouds. So we're just going to count the bonds and count the lone pairs on each carbon. So for this first carbon right here, we have 4 bonded atoms, no lone pairs. So that adds up to 4 charge clouds. And remember, when this is the case, we call this tetrahedral. So I'm gonna okay, what about the next carbon? So we have 4 central atoms here, 3 carbons, and that oxygen is central as well because it has more than 1 bond. This carbon looks, I don't know about you, it looks like the same exact way as the first carbon. So I'm just going to draw an arrow. It's also tetrahedral. What about carbon number 3? It also has the same. So oftentimes if you have central atoms that have the same geometry versus writing the word tetrahedral 4 or 5 or 6 times, you can just draw arrows like that if you want to. All right, let's look at oxygen. What do we have? Well, we have 2 bonded atoms. And we have 2 lone pairs. So that is 4 charge clouds. But what do we call it if it's 2 bonded atoms, 2 lone pairs? Anybody remember? Bent. Okay. So this one is bent. And that's it. We've named all the geometries for this molecule. All right, let's do 2 and 3. And I will let you attempt the other ones on your own. 4, 5, and 6. So first, let's add up the valence. Carbon, we have 2. Each one has 4 valence. Hydrogen, we've got 5. Each one has 1 valence. Fluorine, we've got 1 of those. It's got 7 valence. And oxygen, we just have 1, and it has 6 valence. So that is, again, 26 valence electrons in our structure. Okay, so now let's try to draw it. Draw the Lewis structure, that is. You draw the Lewis structure, start connecting things that are central atoms. Remember, what elements can never be central atoms? We said hydrogens and halogens. These are always going to be branched. So we got two carbons, got an oxygen. Just start attaching hydrogens to your carbons is usually a good bet. And we need to put a fluorine somewhere where this oxygen needs another bond. 2 bonds. Am I done?
No.
What else do I need to do, Aubrey?
Add your lone pairs to your fluorine.
How many does it get?
3.
3 lone pairs on halogens. Okay. Now let's count up. Do we have 26 electrons represented? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I counted 26. Okay. And here's the deal. If some of y'all are like, how in the world is she doing this? I'm having a lot of trouble keeping up. I don't understand this. I don't get it. I'm lost. Reminder again, review the Lewis structure stuff from last Tuesday. You can literally go rewatch that lecture if you want, or portions of it that apply. Shoot me an email. We'll set up an individual Zoom. We can walk through how we're going about these things. There's multiple options, okay? All right, so now we need to name the geometries. So let's look at carbon number 1. It looks a whole lot like the carbons from the previous structure. 4 bonded atoms, no lone pairs, tetrahedral. Carbon number 2, same exact thing. I see 4 bonded atoms. Here's a hydrogen, carbon, another hydrogen, and an oxygen. That's 4 bonded atoms. No lone pairs. That means it's tetrahedral. So we got 4 charge clouds on each of those first 2 carbons. They're both tetrahedral. Now let's look at the oxygen. I see 2 bonds, one right here, one right here. They're both single bonds, so they each count as a charge cloud. So that's 2 charge clouds, plus we have 2 lone pairs. So total, that is 4 charge clouds, 2 bonds, 2 lone pairs. It looks just like the oxygen up here. So that means it is bent. And we're done. We don't name the fluorine, we don't name the hydrogens, we just name the central atoms. Now, it probably seems very ironic that all the carbons were the same and all the oxygens were the same. That's not always the case. Do not get it in your head that carbon's always tetrahedral and oxygen's always bent like this. It may not always be the case, but it just so happened to be for these 2 molecules. Molecule number 3, so we have a nitrogen. One of them, and it has 5 valence. And chlorine, we've got 3, each one has 7 valence. What do you know? 26 again. So which atom, we've got to pick, nitrogen or chlorine, can be central?
Nitrogen?
Nitrogen. How do we know nitrogen?
Because chlorine is a halogen?
And halogens can only form 1 bond. And anything that can only form 1 bond can never be central. So I'm going to attach, and in fact, we know nitrogen it will form 3 bonds. And these chlorines form only 1 bond each. The rest are lone pairs. And then when everything is said and done, nitrogen still has a lone pair too. All right. Count up. Do we have 26? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 20. I counted 26. So which atom are we trying to name here? The geometry, that is. Nitrogen. Sorry, I should be looking at the chat. Nitrogen, yes. So let's look at this guy. I see 3 bonded atoms. I see 1 lone pair. That adds up to 4 charge clouds. And we call this, anybody remember what we call it?
Pyramidal.
Pyramidal. Good job. Okay. All right. So that kind of is the end of our geometry. And again, these other 3 you can practice. We have limited time. We have about 7 minutes left. So we're going to start to talk about polar bonds. And that's probably as far as we'll get. And then I will post videos regarding polar molecules and naming binary compounds. If you've scrolled through the slides, those are the other two topics that looks like we're not going to have time to get to today. I'll post videos on those by tomorrow or Thursday as well. Probably try to do it sooner than later because I think you need that info to do the chapter 4 homework. Okay, polar bonds. So remember covalent bonds. A polar bond is a kind of covalent bond. So remember that we have two kinds of bonds. Right? We have ionic on one side and we have covalent. All right. Now, ionic, there's only one kind of bond. You have cations and anions. But covalent, you have multiple kinds of bonds. You can have nonpolar, covalent. You can have polar, covalent. So we're going to look at the difference between the two. All right. I want to kind of introduce this by actually asking this question right here. What is the difference between the two molecules up top and the molecule on the bottom? And don't just tell me that one is rainbowed and the other is not. What's kind of the chemistry difference? Any guesses? Chat. Somebody said it has a bond thing. Okay, Dallas, what do you mean by that? And then Bailey said it has more than one element, and Bailey is correct. Okay, we've got the same element involved in the molecule on the two up top. We've got a bond between two identical atoms. The line. Dallas, I don't know. I'm going to say sure, but I don't really know what you mean. But Bailey was right. We've got two identical atoms in the molecules up top, and we've got two different atoms in the molecule down below. So the way I like to explain polar bonds is with a tug-of-war analogy. We know that every element has a nucleus. Okay, so if we have two elements, two identical atoms, but the same element in a bond, then what do we know? We know that's two identical nuclei, one on each side of this bond. So if we're talking about hydrogen, we know that we have one proton over here and we have one proton over here in the nucleus of these atoms, these hydrogen atoms. And they're pulling on, they are attracted to the electrons, remember, because these are negative and these protons, we already put the little plus sign, they're positive. So there's an attraction there. So these electrons are being pulled towards that nucleus and they're being pulled towards that nucleus because of the opposite charges. And it just so happens because these are identical atoms, they're being pulled with equal strength. This is like having a tug of war and the two teams are almost identical. Which side is going to win? It's just, no side is going to win. It's just going to stay right there in the middle because those electrons are not being pulled one way or the other more strongly. Same idea with chlorine. Chlorine has 17 protons. So that's like 17 plus charges here. That's like 17 plus charges here. And we've got the negative charge right here. So those electrons are being pulled equally in both directions. All right. So the difference, by the way, is that these molecules, I'm just going to write that out. Have identical atoms in the bond, and this one, the difference was it's a bond between two different atoms. All right, so what that means is that these electrons up here are shared equally. And these electrons are not, or are, I will say, are shared unequally. All right, they are shared unequally. The molecules on the top, they're sharing the electrons equally. So if we imagine a tug of war match now down here, it's like saying we have 17 people on one side and one person on the other, okay? Who wants to be in that tug of war match? So which way are the electrons going to be pulled? If we have 17 plus charges over here and we have 1 plus charge in this nucleus, which way are these electrons going to be pulled? Towards hydrogen or towards chlorine?
Towards chlorine.
Towards chlorine, all right? They're going to be pulled in this direction. Chlorine's going to win. Now, that does not mean that the electrons totally go to chlorine. They're shared. It's just that they're shared unequally. That is where these little signs up here, this partial negative and this partial positive, come into play. What do these mean? Well, number one, this is called partial negative. This is called partial, or you might hear the word semi-negative, semi-positive, partial positive, partial negative. Same thing, partial positive. It's a lowercase Greek delta sign, and then we put the plus or the minus to indicate which side is electron rich and which side is electron poor. If it's got a negative, that means it's electron rich. If it's got a partial positive, this means it's electron poor. All right. So that's a polar bond. A bond where the electrons are not shared equally is a polar bond. A bond where the electrons are shared equally is a nonpolar bond. All right. We'll pick up with other stuff. I'll post videos